Okay, so now we're going to take a look, now that we've introduced some basics, we're going to take a look at how ionic compounds form and then also what ionic bonding is and how it happens in the first place. Now, the one thing that you want to keep in mind when it comes to any type of bonding, whether it's ionic or whether it's covalent, is the reason for it. Okay, so why would an atom want to bond with another atom in the first place, right? There has to be a reason. So why bond in the first place? Right, I think that's a fair question. Right, when you think about bond in chemistry, you can think of it as sort of like the glue, quote unquote glue, that sticks elements together. Okay, so why would one atom or element want to be stuck together to another one, right? There has to be a reason for that. Otherwise, it wouldn't happen in the first place. So why bond in the first place? Well, the driving force behind bonding is stability. Okay, so you want to think about stability, right? And if you keep that as sort of in the background with every topic that we do, that we cover, you'll see that this is at the heart of everything that we study. So when it comes to the periodic table, so on the periodic table, the stability is reflected by having, or stability is due to having a full valence shell. Okay, I shouldn't say on the periodic table. I'm gonna say with respect to electrons. Okay, so WRT, with respect to electrons. Okay, again, WRT means with respect to. So in regards to or concerning electrons, stability is due to having a full valence shell, right? So having that outermost shell completely filled with electrons, that means that that thing is very stable. All the atoms on the periodic table want to be stable, right? Stability is a driving force. Well, the elements on the periodic table that have a full valence shell, so on the periodic table, it's the group 8 elements, group 8A elements, have a full valence shell. Okay, and that means they are very stable, right? Your noble gases are very stable. They don't really react with other elements very easily because they don't need to, right? They are already content. They're happy the way that they are. All the other elements on the table, though, they are not as content. They're not as happy. They're not as stable. They want to be like the noble gases. So two ways by which, or ways by which atoms become more stable is by whichever method. So the other atoms then, or the other elements, can become more stable by adopting or by having enough electrons to be isoelectronic. You know what that term means now, having the same number of electrons as the nearest noble gas to them. Okay, that is a very important statement because we can use that to explain not just ionic bonding that we're going to see now, but we can use it to explain covalent bonding down the road. Okay, it's stability. The elements want to be isoelectronic to the nearest noble gas to be, let me make sure the English is correct here. Other elements can become more stable by having enough electrons to be isoelectronic with the nearest noble gas. Okay, and all isoelectronic means having the same number of electrons, also meaning same number of valence electrons as whatever noble gas, the group 8 element that is closest to them. Okay, that's the driving force. So when it comes to now our ionic bonding, okay, ionic bonding involves, as the name suggests, ions. And ions we've seen can be positive or negative ions. Positive ions we refer to as cations. Negative ions we refer to as anions. Okay. If you think about just intuitively, if you have a positive ion, something positive and something negative, okay, opposite charges will attract. Okay, we saw that way back in week 1. That attraction between a positive and a negative charge, that is the ionic bond. That's all that it is. Okay, ionic bond is just the attraction between ions, between positive ions, negative ions. Another term that you will see being used interchangeably with ionic bond is electrostatic attraction. Okay, big fancy word that just means the same thing, right? Opposite charges attracting each other. So in order for ionic bonds to form, we need ions. We need positive ions, we need negative ions. Guess how those things form, right? Positive ions form. So positive ions, which are cations, form when an atom loses electrons. Okay, and these atoms are going to be typically metals, lose electrons. Okay, your negative ions, which are your anions, so your negative ions, your anions, these form in the opposite way. So these form when an atom gains electrons, one or more electrons. So what types of atoms are going to gain electrons? Well, these are typically going to be your nonmetals. Typically, nonmetals gain electrons. Okay, so those are two general characteristics of things that form positive ions or negative ions. So let's look at some other general statements we can use to help us figure out charges on ions. So we can say that the charge on a main group metal is equal to the group number. Okay, and here we're looking at the A number for the main group metal. So for example, if I'm looking at magnesium, Mg, okay, magnesium is in group 2A. Guess what? Magnesium forms a charge. It's a metal, first of all, right? It will form a cation, positive ion. And what's the charge? It's in group 2A. It'll be 2 plus. Similarly, aluminum. Aluminum's in group 3A. Guess what? Aluminum forms a 3 plus charge, right? Metals form positive ions. And we can use the group number to help us figure that out. We can do something similar for our anions, our nonmetals. When they form ions, anions, the charge on the main group nonmetal is slightly different, but it's still a fairly straightforward case. It's equal to the group number. Okay, and again, this is the A number, the group number minus 8. Okay, so for example, okay, if I look at oxygen, O, right, oxygen is in group 6A. So the charge then on the oxygen ion will be O, and then if I put my charge on top, group number 6 minus 8, right? A little bit of math involved. 6 minus 8 is minus 2, or 2 minus. If you look at fluorine, okay, fluorine is F. Fluorine is in group 7A. Okay, so we have now our F7, group number minus 8, gives us minus 1. And if you recall, we saw that F minus ion up here, right, in our Lewis structure. Now we know why. We understood why this happened in the first place. Now we can quickly get to the same endpoint by using our periodic table to figure that out, okay? So once you have positive ions, negative ions, they are going to attract each other. That is what the ionic bond is. That's all that it is. So what happens then, opposite charges attracting each other, they are going to combine to form a compound called an ionic compound. Okay, so your charges, positive and negative charges, charged ions, will combine, will attract each other. And then the resulting ionic compound must be overall now neutral. Okay, and this is a guiding principle for all of your ionic compounds. When you add together the positive charges and negative charges, you should get 0. Okay, so this means then that the ratio of the cations to the anions, or cations are positive, anions are negative, is shown as subscripts in the resulting chemical formula. So the example that we have up here on top is the simple case of sodium and chlorine, okay? So we have our sodium atom wants to lose that one electron, that valence electron. It forms a charge of +1, right? It makes sense because sodium's in group 1, so it forms a charge of +1. That electron that is lost actually can be taken, can be gained by something that needs it, like chlorine. So the chlorine can accept that one electron to now have and complete its valence shell. When it does so, it adopts a negative charge. Our sodium had a positive charge. Our sodium now and our chlorine, our chloride ion, can combine in a 1-to-1 ratio. Okay, because the 1 plus here will cancel out the 1 minus to give me an overall formula of NaCl, right? The ratio here is represented as a subscript. So subscript after sodium is 1. I have 1 sodium and 1 chloride, 1 Cl. You don't need the ones in a chemical formula. The ones are understood, so it's just NaCl. Right? We saw NaCl back at the very beginning when we introduced ionic versus covalent. So the ratios there are subscripts in the formulas. And those ratios are dictated by the charges. You need the charges to cancel out when you combine your ions. So when you have these oppositely charged species, these ions, how do they actually arrange around each other? Well, you may predict that they're going to arrange themselves such that the positive ions are surrounded by negative ions, again, because opposite charges attract each other, and you would be absolutely right. So for example, if I have some salt, so just imagine some salt crystals, okay, and you were to zoom in on the smallest piece of salt crystal that you have, okay, what you would actually see are billions upon billions of sodium ions and chloride ions that are arranged not in a haphazard way, but in a repeating arrangement of positive and negative ions that we call a lattice. Okay, and a lattice for a crystal here, in the case of sodium chloride, is just a 3D, so three-dimensional array of oppositely charged ions, right? So this is a repeating pattern, in other words, of positive and negative ions in this crystalline structure. So here you can see my sodium ions that are small, they're the gray ones, and then the chloride are green, they're bigger, right? I mean, you saw in the last sections that positive ions, cations tend to be smaller than the negative ions for a whole host of reasons. And we can see now in this crystalline structure, in this crystal lattice, that they are just packed as close together as they can be, because the opposite charges want to be close to negative charge, right? Positive charges want to be close to negative charges, and then that repeats negative close to positive throughout the entire thing. And that repeats billions upon billions upon billions of times. So the energy that is needed to actually convert this solid to the gas phase is something known as the lattice energy. And that is an indication of the stability of that ionic compound. All right, so the lattice energy, we can say, is an indication of stability of the ionic compounds. Stability. So the higher the lattice energy, the more stable it is. So what exactly is the lattice energy? So I mentioned it briefly. So you can think of the lattice energy as follows. So it's the amount of energy required. Okay, so the amount of energy needed to convert 1 mole of the ionic solid. Okay, we're converting this thing into the ions that are in the gas phase. Okay, so 1 mole, the ionic solid into the constituent ions, or their respective ions, that are now in the gas phase. Okay, so in other words, what we're trying to do here is we're trying to take our solid that we have, and we are trying to separate. We're trying to we're trying to pull the ions apart from each other. And if you can imagine now, if the attraction between those ions is very strong, we are going to require a lot of energy to separate them from each other, right? That just makes intuitive sense. You think of two magnets attracted to each other. If there's a strong pull, you need to provide a lot of energy to separate them. If the attraction is weak, you don't need to provide a lot of energy, right? That energy that you provide, that is what the lattice energy is. The amount of energy needed to take that solid now and convert it into the ions in the gas phase. So for example, it's like saying if I have NaCl, sodium chloride, as a solid, I'm going to put my arrow here. That means I'm going to start with the NaCl. We're going to convert it now into a separate now sodium ion in the gas phase, and then the chloride ion Cl minus also in the gases, right? So now I'm separating the gas ions from each other. Okay, so not only am I separating the solid, now I'm trying to convert it into the gas phase. Here, the ions are packed close together. Okay, so the amount of energy needed for this process is the lattice energy. And if you recall, we saw how charges and forces are related according to this equation. I think we saw this back in maybe week 1 or week 2. So the force of attraction here, F, is proportional to, that symbol means proportional to, the product of the charges, okay? So the product of the charge divided by the square of the distance. So D, there's a distance. So D equals the distance between the charges. So just by looking at this general equation, we can make some fairly simple predictions. We can say now, because the product of the charges is in the numerator in this proportionality, we can say that as the charge increases, specifically now as the magnitude of the charge increases. Okay, so that means now as an example, plus 3 versus plus 1. Okay, plus 3 is a greater charge than the plus 1. According to this relation, this mathematical relationship, we can say the force of attraction there is going to increase. Okay, so as the numerator, in other words, get bigger, the force of attraction increases as well. Okay, that we don't have to think too hard about that. We're just looking at it from a math standpoint. So if you have two ions, right, one with a plus 3, one with a plus 1, the plus 3 is going to have a stronger attraction to something, and that should make intuitive sense. The other thing we can see from this relationship is in the denominator here. So if the denominator gets smaller, then the force of attraction is going to get bigger. Okay, so that's something to keep in mind. So we can say that as D increases, F is going to decrease. The force of attraction will be weaker. As D decreases, right? So as the denominator here gets smaller, the force of attraction then will increase. So now you're dividing by a smaller value in the denominator. Okay. So in other words, what this means is if your charges are close together, okay, this is another way of stating it. So if the charges are close together, are close, right? Then the force of attraction is high. And the opposite is true. If the charges are spread out or far apart from each other, then the force of attraction is going to be low. And again, you can think of just some general examples of where that would be the case. Intuitively, that should make sense between them. And we can actually, instead of just, trying to think of situations in our brain, we actually have numbers here to help illustrate that point. So for example, if you compare the first 4 of these, okay, all with the lithiums, lithium fluoride down to lithium iodide, the only difference between all of these is the anion, right? The fluoride, chloride, bromide, and iodide. And what's the difference between them? Well, they all have the same charge, right? They're all F minus, this is Cl minus, this is Br minus, this is I minus. Okay, so they all have the same magnitude charge. The difference here is the size of the anion, because the cation is the same. It's lithium plus. Okay, so what happens to the size as you go down a group? Well, we've seen this trend before. As you go down a group, the size of the atom gets bigger, which means now the charge is spread out over a wider volume, so it's not going to be as strong of an attraction as if we have a smaller ion up here on top. As a result, stronger attraction, higher lattice energy for lithium fluoride compared to lithium iodide where the iodide is a much larger ion. Okay, you can see that with the sodium examples as well. You can see that with the potassium examples also. So that's the where the size or the distance in this case, this would be an example where the distance, so the effect of D on the lattice energy. And the bottom examples, we can see the effect that that the charge has on the lattice energy. So for example, if we look at these two, the sodium oxide and magnesium oxide, here the oxide ions are the same, right? So we have the O2 minus, that's common to both of them. How are they different? They are different in terms of the ions now, right? So the sodium ion is a 1 plus, whereas the magnesium is a 2 plus. Okay, so higher magnitude of charge, we can see here the lattice energy is greater than with one with essentially half the charge. Okay, so the general trend here is what you want to keep in mind. Okay, so as the magnitude of the charge increases, the force of attraction between the ions increases, which means then the end result of that is a higher lattice energy or greater lattice energy. And then we can say as D increases, F decreases. So we can say then as the distance between them, between the charges, between the ions increases, the force of attraction between them decreases, which then would mean the lower lattice energy for this particular scenario. We can also say for the bottom here, if the charges are close together, force of attraction is high. Force of attraction high means higher lattice energy. Okay, so whichever perspective you look at it from, we can use this equation up here to help rationalize the numbers that we see that are experimentally determined. So it actually makes sense. Okay. I think your book does a really good job of illustrating the differences between some similar examples. So here it's kind of breaking down the lithium iodide, sodium iodide, potassium iodide. Here, the common thing is the iodide ion. The difference here is the size of the ion. Okay, as you go down the group, the size of the ion increases. So the distance between the charges goes up, as you can see down here in the denominator. In all three cases, the similar or the thing that's the same is the numerator, which is the charges, right? That doesn't change. The difference here is in the denominator, the distance between the charges, right? And that is that happens when the sizes of the ions change. So larger size here on the right side, okay, which would mean make the denominator a larger number, which would make F then a smaller number. As you can see, smallest lattice energy. If the denominator is small, that would make F a large number, and it would make a large lattice energy as well. In the other example, we can see the difference now in in the magnitude of the charges. And we can see here as the charges, magnitude of the charges increases. So for example, scandium and nitride, 3 plus and 3 minus. So your numerator here is a much larger value. The lattice energy is going to be much greater than where you have just +1 and negative 1 charges.